All right, hello chemists. Today I'm going to show you guys how to draw heat curves and how to do calculations involving heat curves. All right, so here we go. All right, so a heat curve, as we kind of talked about in class a couple days ago, is always going to have this kind of layout, okay? So we're going to have the x-axis and then the y-axis, or y and x. It's always going to go up, flat, up, bigger flat, up, okay? And on the y-axis here, we're measuring the change in temperature, or just the temperature, in degrees Celsius. And on the x-axis here, we're going to be measuring heat added. And added is if we're going to the right, or removed if we're going to the left, okay? So this heat curve we're going to go ahead and do for water, but for any substance it looks pretty much the same: up, flat, okay? So up, flat, up, flat, up. So if this is for good old-fashioned water, we're going to look at a couple things. So the first diagonal down below, okay, this is going to be solid. This diagonal right here, this is going to be for the liquid, and this diagonal up above is going to be for the gaseous state. So I want you to take a beat here. What do I call it when I turn from a solid to a liquid? I call that melting. And right, if I'm going from a solid to a liquid, I'm going in this direction here to the right, so I'm adding energy. What if we remove energy going from a liquid to a solid? We call that freezing. So freezing is going to be to the left there. And once again, this is on the horizontal line. All right, let's try that again. So we're going to go up, 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 up. Now we're at this horizontal line right here. What do I call it when I go from a liquid to a gas? A liquid to a gas. I call that evaporate. Evaporate. So if I add energy, I can go ahead and evaporate a liquid and a gas. And if I remove energy, I'm condensing that substance. So make sure that you have the heat curve for water on your notes now. It should look like this. The last thing I want to make sure is comfortable for you guys is the temperature at which water turns from a solid to a liquid and a liquid to a gas. We've talked about this a lot this week, so hopefully you're comfortable with the fact that at 0 degrees Celsius is when this happens, and at 100 degrees Celsius is when water evaporates. So this is the melting or freezing point of water, and this is the boiling point of water. These graphs are always going to be the same. The temperatures here are going to be the things that end up changing, okay? We're going to use these as a tool to help us figure out when to start and end certain types of heating problems, okay? All right, let's go ahead and move on. Let's go ahead and try our first question here. Draw the heat curve for ethanol. The freezing point is negative 114 degrees Celsius. The boiling point is 78 degrees Celsius. Draw the heat curve for ethanol. Looks like I'm being a little redundant there. All right, let's go ahead and jump into this. So we have our graph, our XY axis here, and this is still temperature. This is still heat added or removed. We'll just go ahead and write added and write to the right here. And once again, this is going to be, I'll change the color here, up, flat, up, flat, up. Okay, so up, flat, up, flat, up. All right, so if the temperature is in degrees Celsius, we know that the bottom is a solid, the middle is a liquid, and the topper is the gas. We know freezing point is when it goes from a liquid to a solid. So right here, this should be negative 114 degrees Celsius. Boiling, remember, is when we go from a liquid to a gas. So we know right here, we know this temperature to be 78 degrees Celsius. So if I ever ask you guys to draw a heat curve, you're just going to draw the up, flat, up, and then you just change what temperature the y-axis is. All right, here we go. Let's go ahead and move on. So a heat curve, right, contains two parts, right? The heat curve is going to be containing a horizontal line and a diagonal line. I'm just going to kind of draw it one more time right here so you can see that there. So at a diagonal line, you're changing the temperature. So at a diagonal, the temperature changes. And the reason that is because we are changing the kinetic energy. So at a diagonal, the temperature changes because the kinetic energy is changing. Remember, the kinetic energy is the energy due to motion. So if you're ever on a diagonal line, the diagonal lines, which are right here, you want to use the equation Q equals mc delta T. Q equals mc delta T. And that's because at the diagonal line, you are changing the temperature. The kinetic energy is changing. So the heat that is being put into the system is changing the temperature. Now, if you notice at the horizontal line, so I'll go ahead and use a different color for this, at the horizontal line, right here, is the temperature changing? And hopefully you see, no, it stays constant, right? As you add energy moving to the right or remove energy moving to the left, the temperature stays the same. So at the horizontal, the temperature does not change. The temp does not change. And why is that? So am I adding energy? Yes, I'm still adding energy, but it's not changing the kinetic energy. You're changing the potential energy. The change is in the potential energy. We're changing the way the chemicals are combined or made up. And so that's where the phase change occurs. That's where the state change occurs. So at the horizontal line, we're going to use one of the two equations that we talked about last class. Q is equal to m times the heat of fusion, or Q is equal to m times the heat of vaporization. So in these situations here, we're using the part where it's solid to liquid or liquid to gas. Okay? So in combination, we're going to be using all three of these equations and determining the total amount of heat absorbed or released by the system to change the temperature of something and also go through a state change. So when we did our lab with the water, right, we melted the ice, all that energy went into melting the ice, the temperature stayed relatively 0 degrees Celsius. Then the water went from 0 degrees Celsius to 100 degrees Celsius, so you changed the temperature of liquid water, and then the water started boiling. And notice it stayed roughly at 100 degrees Celsius because all of that energy is changing from liquid to gas. Let's go ahead and try a question out here. And I'll kind of show you how to use a heat curve, okay? So, boom, 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 boom. Let's go ahead. How much energy is required to boil 50.5 grams of water at room temperature, which is 18 degrees Celsius, about, give or take? So let's go ahead and set up our heat curve here. And we know this is for water. So up, flat, up, flat, up. We know this is for water. So it boils at 100 degrees Celsius and it freezes at 0 degrees Celsius. So room temperature, what state of matter is water? Well, it's going to be a liquid, right? It's right here in the middle. We'll go ahead and kind of map that out here. It's 18 degrees Celsius. So what I first need to do is I need to add energy. To heat up the liquid water to its boiling point. So what temperature is that at? That's at 100 degrees Celsius. So that's the first thing I have to do. The second thing I have to do is I have to add energy to boil that water. And notice the temperature is not going to change there. So I have two equations. I'm going to do first Q equals mc delta T. Q equals mc delta T. And what that's going to do is it's going to heat up the liquid water. So that's going to be 50.5 times the specific heat for liquid water, which is 4.184, times the change in temperature, which will be 100 minus 18, which is going to be, 82 degrees Celsius. So Q is going to be, once again, 50.5 times 4.184 times 100 minus 18 gets us 17,300 joules. 17,300 joules. So in order to heat up 50.5 grams of liquid water to its boiling point, I have to add 17,300 joules. Now here's the thing, I'm not finished. I now need to boil that water. That liquid water is just at its boiling point. So now I need to use the equation Q equals M times the heat of vaporization, which for water is always going to be 2,220 joules per gram. So now I go ahead and say 50.5 times 2,220. And when I go ahead and multiply these two, I'm going to get a pretty large number here. I get 112,100 joules. So boom, step one is heating it up. Step two is boiling. So how much total energy occurred here? Well, the total is going to be Q1 plus Q2, which is going to be 17,300 plus 112,100. Adding these up, 300 plus 112 gets me 129,400 joules. That is the amount of energy that I have to heat up liquid water to its boiling point and also boil it. So there's two amounts of energies required for this. All right. So go ahead and make sure you have all of these steps copied down. And I'm going to have you guys try this one on your own here. Okay. So calculate the amount of energy required to freeze 28.3 grams of liquid water at 0 degrees Celsius, then cool the ice to negative 175 degrees Celsius. I want to point out I have a little bit of a typo here. I just realized I'm going to change this here. How much energy is released? How much energy is released? Go ahead and correct that in your notes. To freeze 28.3 grams of liquid water at 0 degrees Celsius and cool the ice to negative 175 degrees Celsius. I'm going to draw the heat curve with you here, and then I'm going to have you try this on your own. So once again, heat curve is up, flat, up, flat, up. And this is water, so this is 0 degrees Celsius, and this is 100 degrees Celsius. So if I'm starting as liquid water, remember, is this middle part right here. So I'm starting, boom, right here. So the first thing I have to do is I have to remove the energy to freeze it. So right there, this is the removing of energy to freeze the liquid water. Then I have to go from 0 degrees Celsius all the way down to negative 175 degrees Celsius. So by removing this energy here, this is going to be step 2, and the purple is step 1. These are our 2 steps. The equation for step number 1 is going to be Q is equal to M times the heat of fusion. And step number 2 is going to be Q is equal to MC delta T. And the last thing I want to point out, what state of matter is down here? This is a solid. Solid water has a different specific heat than liquid water does. I provided this to you right here. So make sure when you're using this equation, you're plugging that in down below. All right. Awesome. Good work. Thank you so much, guys. And I'll go ahead and see you next time. Have a great day. Bye-bye.